Hi, my name is Evan. I'm a senior, and we're Canyon Crest Academy, also known as the Red Tie team.
I'm Jonathan. I'm also a senior.
I'm Steven. I'm also a senior.
I'm Larry. I am not a senior.
And I'm Michelle. I am also a senior.
Okay, does this work? Okay. So hello, everybody. Today we'll be doing our presentation on our solution to this year's M3 problem, A Tale of Two Crises, the housing shortage and homelessness. So briefly, before we go over our solution, I'd like to go over a brief overview of our problem. So we were to use math modeling to provide insights into the housing shortage and homelessness crisis in various cities. For us specifically, we focused on Seattle, Washington, and Albuquerque, New Mexico. And in the first two parts, we were to predict the housing supply and homeless population in those two cities. And in the final part, we were to construct a model that would help cities develop a solution. And one thing we assume throughout this problem is that the economy will remain roughly stable as it has in the past, where it follows a business cycle of around 6 years. In this assumption, we pretty much assume that real GDP will grow roughly linearly. And now I'll pass it off to Jonathan, who will present Q1. It was the best of times.
Thank you, Evan. As he said, the first part of our problem is to estimate the total housing units for the two cities, Seattle, Washington, and Albuquerque, New Mexico. And we want to do so for the next 10, 20, and 50 years. So before we begin, I'd like to first make a few assumptions. First, there are no significant governmental policy changes, natural disasters, or any unforeseen influences related to the housing supply growth in either of the two cities. And this is because these are very hard to predict, so we're going to assume that they're not going to happen. Next, the housing supply increases proportionally to the city population growth. As the city population increases, naturally there will be more demand for housing supply, and that will also increase. Our third assumption is that the population growth in all US cities are roughly linear, and we'll justify this in the next slide. Our fourth assumption is that the housing supply data is homoscedastic, which means that the variance does not increase over time. And finally, our housing supply growth will be roughly linear, which is derived from the second and third assumptions. So the reason why we think that the population growth in US cities is roughly linear is because after plotting the past 70 years of the US population data and calculating the line of best fit, we found an R-squared value of 0.997, which is a very strong correlation. And so we're confident that in the next few decades, the US population will continue to grow roughly linearly. Here's the data that were given by the M3 challenge. On the left is the Seattle data, and on the right is the Albuquerque data, and we're given the data from 2010 all the way up to 2022. And we are trying to fit this onto a univariate linear regression model following the equation y equals ax plus b, where a and b are the constants that we're trying to adjust, x is the year, and y is the housing units that we want to try to predict. So after fitting our data onto the univariate linear regression model, we project the following results. Both Seattle and Albuquerque project a positive growth in housing supply, but Seattle's grows significantly faster. To test the robustness of our model, we conducted a sensitivity analysis where we removed the 2022 year data point, and we refit our data onto a new model, and we compared the data between our predicted data and our actual data. The actual data is labeled here in pink, while our predicted is the green one. And after calculating the error, we got an error of 0.81% for Seattle and an error of 1.74% for Albuquerque. So these are very, very small errors, and we're confident that our model is working. So now to discuss some strengths and weaknesses of our model. Some strengths include it being easy to understand and interpret, and also because it takes the average of the housing supply, it's less sensitive to outliers and any unforeseen influences if they do arise. However, it is less sensitive to the more complex relationships between housing supply and population growth, and because we're also assuming that the housing supply grows roughly linearly, that could also not be true, even though it has shown that trend in the past 70 years. And finally, recent data has been affected by a one-off event, which is COVID, and that could have skewed our data one way or another. Next, I'd like to bring it to Steven to talk about Q2, and as well as Larry to talk about Q2. It was the worst of times.
Thank you, Jonathan. So the task of Q2 is to predict the homeless population in 10, 20, and 50 years for the same cities, Seattle and Albuquerque. So in our approach to this problem, we made a few assumptions. The first is similar to Q1, where we assume there are no sudden external influences on homelessness, and this is because it is difficult to predict, and thus we will not account for them. The second assumption is that out of all factors of homelessness, we only consider the following four, which are housing price, real GDP, poverty rates, and the city's current population. This is because it is very difficult to try and account for every single factor of homelessness, so we identified these four as the major ones. Finally, we assume that each of these factors have a constant weight of influence. This means, for example, if we consider housing price, its impact on homelessness, relatively, it does not change between like 1 to 5 or 10 years. So with these assumptions, we have two parts in our model. The first is that for each of the factors, we make a linear model to predict their value for a given year Y. And the only adjustment is on poverty rates because its unit is a percentage. So it makes sense for it to not change as much within a short period of time. But otherwise, we have linear models, use them as inputs, and they're scaled by some constant C's. And then we combine them in a multivariate model in order to predict the homeless population. So now I invite Larry Wu to explain model results.
Okay, so after modeling the independent variables, we see that we get these 4 graphs for Albuquerque. Notice that 3 of the trends are increasing, and the only one that's decreasing is poverty percentage by year, which is decreasing and notably not linear. And for Seattle, we see a very similar thing happening, except the scales are different and the curve for the poverty percentage is different. So after using these independent variables to model our final homelessness population, using the multivariate model, we see that the Seattle population trend is increasing and the Albuquerque is decreasing, mainly because the homeless populations we were given had those trends. So we can see that in 10, 20, and 50 years, we have these populations predicted. And so we conducted a sensitivity analysis of our data. So we removed the last year's data point that we used in our data. Note that some of the data points are missing because we noted that they had bad data collection as noted by other people. And so in the end, we removed the data point and then we refit the line. So we see that we get an error of 4.46% and 17.31%. So to discuss the strengths and weaknesses of our model, so for our strengths, we note that the multivariate linear regression satisfies our assumptions pretty well because each factor has a roughly constant weight that affects the homelessness population, which is what we assume to be true. And in addition, in the long term, since it's a linear model, the predictions won't grow exponentially or even like quadratically. They'll stay roughly the same order of magnitude as what the homeless population will probably be. And also, since it's a multivariate linear regression, it's very easy to interpret and understand the results. For our weaknesses, it's limited to the defined factors that we chose, the 4 major ones. And in addition, it potentially oversimplifies each factor's effects by assuming that each factor impacts the homelessness population linearly. However, this is most definitely not the case, but we can still model it linearly as a rough approximation. And in addition, similar to Jonathan's data, the recent data is affected by a one-off event called COVID. Yeah. So next, I will bring it to Michelle and Evan to discuss Q3.
Thank you, Larry. Now, for question 3, we are tasked with developing a tool to help cities address homelessness in the long term. And for this question, we'll be focusing on the city of Seattle over a period of 10 years. Now, a good solution to homelessness should reduce the cost of chronic homelessness on the city in the long term. And hence, we choose to study permanent supportive housing, or PSH for short, as our solution to homelessness because it has already been partially implemented in Seattle and hence has more available data. Furthermore, PSH has historically proven to be relatively effective in keeping people off the streets in the long term. Additionally, our model should be flexible in the face of different environmental circumstances. And to achieve this, we'll be implementing a sort of modified Markov chain. But first, some assumptions. We first assume that when we are developing a plan to address homelessness, the primary limiting factor to a city is the cost, because cities' budgets are limited. Furthermore, we assume that a comprehensive PSH program can be implemented by a city to address the homelessness issue, as we will be simulating the effects of such a policy. Furthermore, we assume that the population of Seattle can be loosely categorized into 4 groups: the non-homeless, the temporarily homeless, the chronically homeless, and those currently in PSH. Lastly, we suppose that individuals currently in PSH will either sort of return to being homed or remain in PSH. In particular, they will not revert to being chronically homeless, as because mentioned earlier, PSH has historically shown to be fairly effective in this task. And now I'll pass it to Evan to talk a little bit more about our model.
Okay, thank you, Michelle. So now I'll be going briefly over our motivation and actual model. So in this model, we chose to use a Markov chain. And the reasoning for this is because it allows us to essentially put this city of Seattle into a vector. And pretty much what we can do this vector is perform matrix multiplication, which allows us to model the interactions between various groups, such as someone falling from non-homelessness into homelessness. And then it allows us to basically condense these interwoven relationships into one simple model. And this also allows us to iterate easily month after month and also quickly adapt to any given population or circumstance, since we can adjust the matrix or vector as necessary. One thing to note about our state model or Markov chain is that we did establish earlier, as Jonathan mentioned, that we assume that population will increase linearly over time. And so to adjust for this, we chose to add a constant amount of non-homeless individuals to the population each month to adjust for population growth. And we repeat this process every month. So here's our actual model. So essentially what we do is we take the 4 groups that Michelle defined earlier, such as non-homeless, temporarily homeless, etc. And then we put them into a vector and we multiply it by our matrix. All these numbers come from various sources about homelessness in Seattle. And once we're complete with that multiplication, we then add our population growth as mentioned earlier, and this gives us the next month's population. After this, we need to calculate the cost to the city per month, and to do this, we perform a simple linear cost calculation where we assume non-homeless individuals, for example, do not have any impact on the city's homelessness budget, whereas someone who is chronically homeless, for example, might have around the $3,000 impact on such a program. And now I'll turn it back to Michelle to talk a bit about the sensitivity analysis and results for this model.
Thank you, Evan. Now, for sensitivity analysis, we will simulate several different environmental circumstances and observe how the homelessness statistics change in the long term. Now, these graphs are derived by plotting time against homelessness data, which is obtained by repeatedly iterating our matrix multiplication across several months. Now, in the top row, we see the effects of no policy change on the right versus major policy change on the left. And in the former, we see that homelessness continues to grow along with the population of Seattle, while in the latter, we see that homelessness is greatly reduced, coming with a reduced cost as well. Now, in the bottom right here, we see the effects of a major recession in which temporary homelessness and chronic homelessness briefly spike for a while before dropping back to an equilibrium level. And we see that this results in a lot more net cost, but is still vastly better than no policy. Furthermore, in the bottom left, we simulate the effects of a natural disaster, in which case we have a surge of temporarily homeless individuals, but this once again quickly drops to reasonable levels. And this makes sense, as those who are temporarily displaced by a natural disaster are likely to have support infrastructure in place that can help them quickly reclaim a residence. Now, we see that PSH is a generally effective solution across a variety of scenarios, and we see that PSH has the potential within 10 years to save hundreds of millions of dollars based on our graphs. And so regarding our model, some strengths of it include that it is robust in the long term and across a variety of circumstances. Furthermore, it is customizable and versatile, as city leaders can tweak the variables to suit their own situation. And though in our case we only test PSH, the same model framework can be adapted to test other solutions to homelessness as well. Some weaknesses, however, are that there are a lot of unforeseen logistical issues that can arise when trying to implement a policy like PSH in the real world that we do not account for. Furthermore, homelessness is not the best documented, so some of our concepts may be sort of inaccurate to the real situation. And finally, I'll pass it off to Evan to finish us off.
Okay, so now I'll briefly be going over a summary of what we've explained so far. So in Q1, we were tasked with predicting housing supply for both Seattle and Albuquerque. And so for this, we predicted that in both cities, it would exhibit linear growth. And therefore, we found that in Seattle, housing supply, both Seattle and Albuquerque have housing supplies expected to increase, but Seattle's will grow at a much more rapid pace. In Q2, we were tasked with doing much the same thing, just with homeless populations, and using a multivariate model based on linear, single variable linear models. we found that Seattle's homeless population was expected to increase, whereas Albuquerque's is expected to decrease. And finally, for Q3, we constructed a foundational model and a foundational and easily adjustable model for the movement in and out of homelessness. And for this, we used a custom Markov chain to identify the cost of homelessness in any given month, as well as the impacts of certain policy changes, as well as events like natural disasters. And we determined that permanent supportive housing is a potentially viable and cost-effective solution. Thank you all for listening. Yeah, so we'll be taking questions.
Great, thank you. Suzanne, you can start with a question if you have one.
Thank you. All right. Thanks very much for your presentation, and I appreciate the coordination and attention to detail with your outfits and a little flair, so that's really nice. So you said, one of the last things you said is that your models predict that the homeless population will decline in Albuquerque and the opposite in Seattle. What are your thoughts about that? Why did it turn out that way?
I think this is mainly because the homeless population was the dependent variable, and even though the independent variables had the same trends, the dependent variable data that we had showed differing trends. So in Albuquerque, it was overall decreasing, and in Seattle, it was increasing. So this is why the outcomes were different.
And is there anything in, let's call it real life, separate from the bit of data that you have, that makes you think that that would be the reality, that one would increase and the other decrease by any chance? And the answer could be no.
I mean, one of the things we did kind of consider is that Seattle is a very fast-growing city, and generally that means that there's a lot of opportunity, but also it means that since there's so many new people coming into the city, maybe the resources might be more strained than somewhere like Albuquerque, where it's remained relatively stable in the past few years.
Okay, good, thank you. And then I actually have a couple of questions, and I'll only ask one, I guess. At some point with the sensitivity, I think you did this twice. You talked about removing a point, a single data point, and it seems like you only did that for the set of data. You removed the last bit of data, right? Is there a reason you only removed the last bit of data and you didn't, remove, some in earlier years and test things out?
So like the most recent data is like partially impacted by COVID. So like we thought like since it was a semi-special event of a point, it might be more insightful to try and remove that one compared to other points.
And along the way, did you remove something in the middle just to see if it was significant? Any chance?
We did not try considering that, but
Okay, all right, thank you.
Yeah, I have a question at part one. So you modeled population growth with a linear model. And in your paper, you do have residual plots. In your presentation, you didn't. Like, could you comment what is that residual plot and what, in general, is it used for?
Yeah, so we mainly didn't put the residual plot on here because of the time constraint. I would obviously want to explain more about it. And the residual plot on the paper, there did show a kind of a parabolic trend, and although there was this kind of pattern, because the scale to the actual U.S. population was so small, we justified the fact that that's why the residual was roughly we are confident that the residual has no effect, and so that the U.S. population grows linearly. Yeah.
Did you look at the residuals for other models?
Yeah, we did try quadratic regression and other exponential models, and they gave us worse outcomes like R-squared values and other things. And so that's why we chose a linear model. Yeah.
So you chose by R-squared.
Yeah, R-squared, and also the fact that the economy grows at a roughly linear pace, and also everything else. Yeah, so we're pretty confident that it's growing linearly. Yeah.
Yeah, so to reiterate what he said, it is true that in our residual plot, we noticed a sort of sinusoidal pattern. And this actually we expected, given that we know the economy follows sort of inflation and recessionary periods. However, we did not believe that it was suitable to fit a perhaps more convoluted model to get this pattern to match because we felt that given the limited amount of data points, which is only 13 or so, we cannot very accurately capture these variations by modeling onto them. And like fitting our model onto these variations would just make it more likely to be inaccurate in the long term as the phase gets shifted. And so we believe that, yeah, as we said earlier, a linear model is generally accurate and less sensitive. Yes, there is a pattern, but this pattern is sort of inevitable, and we do not have enough data to accurately predict the seasonality.
Thank you.
I have a follow-up question on Suzanne's first question. So we saw the downward trend for Albuquerque, downward predictions for Albuquerque, and the upward ones for Seattle. And I buy your explanation that this is because the dependent variable is going down for Albuquerque. But it's a small amount of data. It's like, I don't know, 15 years or something. And if you look at it, it's sort of like a U shape. So I get a little concerned that I would be concerned if the model is too sensitive to that negative linear trend in Albuquerque, because yeah, that's a great picture exactly on the right. It's sort of iffy whether this is actually going down. So I guess you have a limited amount of time, so I think what you did is reasonable. Given more time, how could you incorporate more data into the model to reduce the sensitivity?
So I think as you can see, the first few years have like a pretty strong downwards trend, and then after that it seems to be increasing. So if we had more time, we would probably like split up the data and try to analyze it that way.
Yeah, so like, I think for our model, we analyzed the effects of different factors on the homelessness population of Albuquerque. We can possibly also experiment more with using past statistics to analyze it and do perhaps something similar to Q3 where we model how these sort of groups interchange and affect each other.
Can I follow up on that?
Yeah.
So the variables used were housing prices and poverty rates. I was wondering if you looked at the relationship between those variables or thought about if there's something else that's impacting those variables.
Yeah, so as you mentioned, we did only look at these 4 factors. The main reason we kind of didn't really focus on anything else is 1, the time restraint, and 2, as we mentioned, we can't really consider every factor, or that makes our model kind of too convoluted. If we had more time, we definitely would have considered how these factors would have impacted each other. I think that's very important, and it's kind of one of the reasons we didn't focus on, we didn't use like our model for Q1 as an example, is because we believe that housing price is kind of also based on housing supply, and considering housing supply as well might have been like double counting that effect.
Yeah, this is also one of the reasons why we didn't include income, because we thought that poverty percentage would have covered that.
Any further questions?
Any other questions?
May I ask a question?
Absolutely.
I would like to say thank you for flying the UGA colors. So
Anyway, do you guys have a favorite bird?
A favorite bird?
Yes.
Favorite what?
Favorite bird?
Yeah, birds. Like,
I like canaries, because I had a canary when I was a kid. Any other favorite birds, judges? No. They just don't like birds.
it's hard to narrow down to one.
Hummingbird. Hummingbird
That's a good
would be
answer.
my answer.
Okay, thanks, guys.
thank you.